Welcome back. After building the first part of the Natures project, it's now time to take a look behind the scenes of CSS, to really understand how CSS works together with the browser to display the web pages that we built. The students in my JavaScript course really appreciated these kinds of lectures, and so I decided to include this more conceptual content in the CSS course as well. And this is so extremely important because getting started with CSS is actually very easy. But really knowing what's going on behind the scenes is completely different, and it's really not as easy as getting started. So in this section, we're going to talk about a couple of really important and advanced concepts that you need to understand if you're serious about CSS, and if you want to take your skills to the next level. Okay? What you're going to learn over the next couple of lectures will really set you apart from many CSS developers out there, who many times simply don't have all this knowledge. And I myself had to learn these things the hard way over many years, believe me. And so it's great for you that you can learn it in like just an afternoon or something. And I promise you that these lectures are not boring, okay? I really tried to make them as exciting as possible. And we're also going to immediately apply some of these concepts to the project as we go through these lectures. So I'm really excited about the content in this section, and I hope you're going to find it really helpful as well. Now that we have our project all set up, let's talk about three important and fundamental principles that we need to constantly keep in mind if we want to build good modern websites or web apps with HTML and CSS. And I call them the three pillars of writing good HTML and CSS. Now, this lecture is not exactly about coding, but it's absolutely crucial that we talk about these principles here right in the beginning of the course, so that we start off the project without making any mistakes we would then have to fix later down the road. Alright, so the three pillars are responsive design, writing maintainable and scalable code, and caring about web performance. But let's look at them one by one. So, the first principle is responsive design, or responsive web design, which simply means that we build one website that works beautifully across all screen sizes on all devices. But I'm sure you already know that, right? So responsive design is absolutely a standard today, and so there is no way you're going to build a non-responsive website in 2017 or even later. Now, if you're taking this advanced course, then I assume that you already know at least the fundamentals of responsive web design, things like fluid layouts and media queries. But we're going to take it one step further in this course, because modern responsive design also includes stuff like responsive images, which is a huge topic itself, using correct units for things like font sizes or element dimensions, and it also includes having either a desktop first or a mobile first strategy. And we're going to talk about all of that during the projects of this course. Next up, we need to talk about writing maintainable and scalable code. Now, this is actually more important for you, the developer, than for the final user of the website. But it's still something we need to follow if we want to build a good website. So, writing maintainable and scalable code means to write code that is clean, easy to understand, that supports future growth, and above all, that is reusable for you as well as for other developers who might take on your project in the future. So, if we want to write maintainable and scalable code, we need to care and think about our CSS architecture, which is the way we organize our files, how we name our classes, and how we structure our markup in HTML. Now don't worry if all of this sounds weird or complicated to you, because it's really not, and we'll talk about this stuff in a separate lecture a bit later in this section. What I want you to understand for now is that this stuff is really important if you want to step up your game and become a more professional CSS or front-end web developer in general. Writing maintainable code is something that all professional web developers care about a lot. Alright, and last but not least, let's talk web performance. Making a website or app more performant means to make it faster and to make it smaller in size, so that the user has to download less data. Now, there are many things that affect performance, and some factors don't have much to do with our code, but some of the things that we can do is to make as little HTTP requests as possible, meaning that we should include as little as possible files in our HTML document, write as little code as possible, of course, compress our code, and use a preprocessor like SASS that we're going to explore later in this course. Now, this is all great, but maybe the biggest impact we can have on performance is to actually reduce the use of images, because images are usually what makes up by far the biggest part of the size of a website. We can do so by using only images that are really necessary for a website or app, and also by compressing these images so that they use less bandwidth for the final user. Okay, so these are the three pillars that we will have in mind all the time while building our projects. We have to always ask ourselves if the code we're writing is responsive, if it's maintainable and scalable, and if it affects web performance. Hello and welcome back to a more conceptual lecture this time. And this is probably one of the most important lectures of the entire course. I promise you that we're going to go back to some serious coding after this section, but since you signed up for an advanced CSS course, we need to get into some advanced stuff before moving on in the course and in our project. Now, I couldn't really call this course an advanced CSS course if I wouldn't show you some of the stuff that happens behind the scenes of CSS as we load the web page, right? Now, most, if not all the other courses out there, they just teach you the coding stuff itself. But in my courses, I like to teach you how stuff actually works, and the important concepts that you need to understand in order to become a better web developer, and in this case, a better CSS developer. That's what I did in my JavaScript course if you took that one, and that's what I do in this course as well. So let's take a look now. And we start by asking what actually happens to our CSS code when we load up a certain web page in a browser. Now, a bunch of stuff happens behind the scenes of the internet until the browser can actually start loading that website we requested. Things like HTTP requests, figuring out the right domain name service, etc. We're not going to focus on all of that though. Instead, we're only interested in what happens in the browser on a computer where the user opens the page. So our starting point is when the browser actually starts to load the initial HTML file. It then takes the loaded HTML code and parses it, which basically means that it decodes the code line by line. From this process, the browser builds the so-called Document Object Model, or DOM, which basically describes the entire web document, basically like a family tree, with parents, children, and sibling elements. So this Document Object Model is where the entire decoded HTML code is stored. Now, as the browser parses the HTML, it also finds the style sheets included in the HTML head, and it starts loading them as well. And just like the HTML, CSS is also parsed. But the parsing of CSS is a bit more complex, and that's why we'll talk about that in great detail in the next lecture. For now, let me just tell you that during the CSS parsing phase, there are two main steps. First off, conflicting CSS declarations are resolved through a process known as the cascade. The second step in the CSS parsing is to process final CSS values, like, for instance, converting a margin defined in percentage units to pixels. Imagine that we define a left margin as 50%, but that 50% on a smartphone is completely different than the 50% on a large screen, right? And that's why these percentages and other relative units can only be calculated on the user's device in the parsing phase. But again, we're going to talk more about that over the next lectures. And of course, I'm going to show you all of this in code as well, because that's obviously the whole point of learning all of this. Alright, now after all of this is done, the final CSS is also stored in a tree-like structure called the CSS Object Model, similar to the DOM. And now that we have the HTML as well as the CSS parsed and stored, these together form the so-called rendered tree. And with that, we finally have everything we need to render the page. Now, in order to actually render the page, the browser uses something called the visual formatting model. This algorithm calculates and uses a bunch of stuff that you already know about, like the box model, floats, and positioning. We're going to talk a little bit about how this visual formatting model works in one of the next lectures, because this actually has a lot to do about how we write our code. So stay tuned for that lecture. Okay, and so finally, after the visual formatting model has done its work, the website is finally rendered or painted to the screen, and the process is finished. Great! So now you understand what happens behind the scenes of a page load in a browser. And over the next couple of lectures, you're gonna understand it even better and even deeper. So, I hope that you're curious now, so let's move on to the next lecture right now. Hey there! So in the last lecture, I gave you a high-level overview about how HTML and CSS are processed in the browser. Now in this lecture, we're going to start to look at the CSS parsing phase, because a lot of important stuff happens in this phase. Now, just before we start, let's do a quick review of the official terms that we can find in a CSS rule, just so that we're all on the same page in these lectures and the coding videos. So, a rule consists of a selector and a declaration block. As you know, we use a selector to select one or more HTML elements that we want to style. Then in the declaration block is where we write the actual styles in order to style elements on our page. To do so, we can write one or more CSS declarations in each declaration block. Each declaration consists of a CSS property and its corresponding value, which is the value that we assign to a property. This value we assign to a property is called the declared value. Alright, and that's it. Very simple. So let's now talk about the first step of the CSS parsing phase. First off, remember that in the parsing phase, the first step is to resolve conflicting CSS declarations, and the second step is to process the final CSS values. So let's start with step 1 in this lecture, which is the cascade, and let's define exactly what it is. So, the cascade is the process of combining different style sheets and resolving conflicts between different CSS rules and declarations when more than one rule applies to a certain element. Because, as you probably already know, a declaration for a certain style property like font size can appear in several style sheets and also several times inside one single style sheet. Now, CSS can also come from different sources. The most common one is the CSS that we, the developers, write. These declarations that we put in our style sheets are called the author declarations. Another source can be the user declarations, which is CSS coming from the user. For instance, when the user changes the default font size in the browser, then that is user CSS. And last but not least, there are the default browser declarations. For instance, if we put an anchor tag in our HTML for a link, and then don't style it at all, it will usually be rendered with blue text and underlined, right? That's called the user agent CSS, because it's set by the browser. So the cascade combines the CSS declarations coming from all these different sources. But how does the cascade actually resolve conflicts when more than one rule applies? Well, what it does is to look at the importance, at the selector specificity, and the source order of conflicting declarations, in order to determine which one takes precedence. And here's how that works. First off, the cascade starts by giving the conflicting declarations different importances, based on where they are declared, so based on their source. The most important declarations are user declarations marked with the important keyword. You already know the important keyword in CSS, right? If not, I'm going to show you an example in a second. Next, the second most important declarations are the author declarations marked with important. Third, the normal author declarations, then the normal user declarations, and finally, the least important ones are the default browser declarations, which actually makes a lot of sense, so that we can easily override these declarations coming by default from the browser. But we should better look at an example here, right? So here we have two rules which both apply to the button class, and we have two conflicting declarations about the background color. These are both author declarations, but if you look closely in the first rule, the declaration with the blue background color contains the important keyword, and therefore this declaration is more important, as we can see from our table. This means that this is a declaration that gets precedence, and so we see that our button is indeed blue. Great! Does it make sense to you? I'm sure it does, and we'll see a lot more examples later on. Now, a lot of times we will just have a bunch of conflicting rules in our author style sheets without any important keyword. That is actually the most common scenario, and in this case all the declarations have the exact same importance. Now, what happens in this case? What the cascade does if this is the case is to calculate and compare the specificities of the declaration selectors. And this is how it works. Inline styles have the highest specificity, followed by IDs, then classes, pseudo-classes and attribute selectors, and finally the least specific, the element and pseudo-element selector. So, when we have conflicting declarations with the same importance, as we saw in the last slide, we calculate their selector specificity based on the priorities I just showed you. But let's see how we actually calculate specificities with a small example. That's always best, right? First off, all these declarations have the same importance, because they're all author declarations. So let's calculate their selector specificities in order to find out if the background color will be either blue, green, purple, or yellow. And this is how we do it. The specificity is actually not just one number, but one number for each of the 4 categories I showed you before: inline styles, IDs, classes, pseudo-elements and attributes, and finally elements. And for each of these, we count the number of occurrences in the selector. Simple as that. So, here in selector 1, we don't have any inline styles, of course, because an inline style has to be written in the HTML, which is not the case here. So it's a 0. We also have no IDs here, so it's again a 0. But we do have one class, the button class, and so for the classes category we have a 1. And finally, there's no element selector here, so 0 for that one as well. And that's it. This selector specificity is 0, 0, 1, 0. Great. Let's now compare it to the others. The next one is also not an inline style, so 0 for the first one. Now, here we actually have an ID selector for the nav ID, right? So it's a 1 for the ID. We also have 2 classes, pull right and button, so it's a 2 for the classes category. And finally, there are also 2 element selectors here, the nav element and the div element, which means that it's also a 2 for the elements category. So finally, the specificity to this selector is 0, 1, 2, 2, which is actually a highly specific selector. Selector number 3 is very simple. It's just an element selector, and so the specificity is 0, 0, 0, 1. And now the last one, selector number 4. First again, we have the nav ID, so it's 1 for the ID. Next, we have a class, the button class, and also a pseudo class, which is hover, which makes it 2 for the classes category in total. And since there's also one element selector, the final specificity is 0, 1, 2, 1. Make sense? Now, you're probably wondering, well, this is all great, but how do we actually use these numbers to find out which of the selectors applies? We start to look at the numbers from left to right, starting with the most specific category, the inline styles. If there is a selector with 1, it wins against all the other selectors, because this is the most specific category. Well, this is not the case here, so let's move on to the IDs. We see that selector 2 and 4 have a 1 here, while the others have 0. So the ones with 0 are out of the game, because they are less specific than selectors 2 and 4, the ones with the IDs. Okay? Now, since both selectors have a 1 in this category, we have to move on and check the classes. They both have a 2 in this category, so it's still a tie between them. And finally, in the elements category, the selector 2 has a 2, while the selector 4 has only 1. And so we have a winner here. The selector number 2 is the most specific selector of all, and so it will give our button a green background. The value of the winning declaration is called the cascaded value, because it's the result from the cascade. So, we start with a bunch of declared values, in this case blue, green, purple and yellow, and one of them wins and becomes the cascaded value, which is in our example green. Now imagine selector 4 also had 2 elements. Then both selectors 2 and 4 would have the exact same specificity, right? So, what happens in this case? And I promise you, it's almost over now, okay? Well, if there's still a tie at this point, then the last CSS declaration written in the code is the one that will apply. So again, if everything is equal, if all the declaration selectors have the same specificity, then it's simply the last declaration that will be used to style the selected element. That's it. Now, just before we finish this lecture, let me give you a quick summary and overview of the most important things we just learned. This is essentially what you should really retain from this lecture. First off, we learned that CSS declarations marked with the important keyword have the highest priority when multiple declarations are in conflict. But you should only ever use important as a last resource. If something doesn't work the way you think it should, then look at your selector specificities and figure out what's going on. That's always better than just adding important, which may solve the problem in an easier way, but will cause you problems in the long run. Remember the talk about maintainable code? Well, thinking about specificities and using important only as the last resource is one of the things that will make your code more maintainable for the future. The next thing to remember is that inline styles that you write in your HTML will always have priority over styles you write in an external style sheet. But since using inline styles isn't such a good practice anyway, this one isn't all too important. Next, a selector that contains even only one ID is more specific than one with 1,000 classes. So if you want to be really specific, use an ID. In the same way, a selector with one class is more specific than one with 1,000 elements, of course. One thing that is really important to note is that the universal selector has no specificity value, and so it's 0, 0, 0, 0, which means that all other selectors have a precedence over it. We will see how and why when we start coding our project. Another thing that you should note is that it's best to always rely more on specificity than on the order of selectors. This way, if you someday rearrange all your CSS code, you won't have any surprises which could mess up your entire code. This again makes your code a lot easier to maintain, which is hugely important. Now, there's actually one case where you do need to worry about the order of selectors, and that's when you're using external third-party style sheets. Imagine, for instance, that you include something like a reset style sheet, which defines a couple of styles for common elements. In this case, of course, you want your style sheet to be able to override those third-party styles if necessary. And so your own style sheet should be the last one to be included in the HTML. So in this case, the order is actually hugely important. Alright, and that's actually all there is to know about the cascade and specificity in CSS. So if you ever wondered what the cascading word in cascading style sheets actually means, now you know it. Great, right? And the best part is that understanding all of this will now allow you to write better, cleaner and more maintainable CSS code. So we talked about the cascade and specificity in the last lecture, and these concepts can absolutely be a bit hard to grasp. So let's now look at an example that I prepared for you and which is actually pretty similar to what we looked at in the last lecture. In order to do that, let's open a code pen so that I can quickly experiment with some code. Now, in case you're not familiar with CodePen, it's just a very simple web app where we can input HTML, CSS and JavaScript code and experiment with it, and it will then render the result down here, okay? So if you want to follow this quick example, then just go to CodePen, codepen.io, and it will probably, here, so create a new pen. And then you can just copy the code that I have in my CodePen here. So just pause the video and copy the code if you want, but it's, I think, not really necessary if you don't wanna. You can just watch me explaining stuff here in this CodePen that I have prepared already. So this is again similar to the example that we had in the previous slide. So down here we have the don't click button. So we have 4 selectors here that actually select this button and try to give it a different background color. So we simply have the button class selector here, then we have the anchor element selector, we have this huge crazy selector here, and then we have this one here which actually has the hover pseudo class. So let's see what happens. So as we already saw, this one has a pretty low specificity, right? Because it has just one class. And this one here even worse. This has almost like the lowest specificity possible. And so these blue and purple color, there's almost no way that we can have this color here on the button. But there is one way though, right? Remember? Because even if the specificity is really low, we can give these declarations a higher importance, and then the specificity doesn't even matter, because if they're more important, they will be applied. And so for example, if we put an important here and wait till it updates, then here, right, we have the purple color that we specified here. And so now, even with the lowest specificity possible, we have the purple background color simply because we made this declaration more important than all the others. And the same thing would of course work if we put it here. Just to show it to you, of course it turns blue. Now I already mentioned that we shouldn't really use this important unless there's something really weird going on in your code. But usually if you need to use important, then that's a pretty bad sign, and you should probably go back and refactor your code and change some stuff in there. Now what I really wanted to show you though is these two selectors down here. So you see that currently this declaration here is the one that applies, because this selector is the one with the highest specificity of these three. Not counting this one here right now because it's on a hover state. So this is supposed to only turn yellow when we hover the button. Now what actually happens when we now hover the button? Let's try it out. And it doesn't turn yellow, right? Even though we specified here that the button, when it's hovered, should turn yellow. So why is that happening? And it is happening for a very simple reason. Because remember that pseudo classes also count into the specificity. So this one here counts 1 into specificity. Now if we do the math of this selector, which has one ID, such as this one, it has 1 and 2 classes, and this has also 1 and 2 classes, because this one counts as if it was a class, but then this one has 2 elements, and this only has 1. And therefore, this selector here is more specific. So again, it has the same amount of IDs, the same amount of classes, but this one here has 2 more elements, div and a, while this one only has 1. And so no matter if it says hover or whatever it says here, this one is more specific, and therefore it's the one that applies, not this one. No matter if you hover it or not, the specificity is lower, and so it cannot be applied. If we want the background color to be yellow, then we will need a selector which has an even higher specificity. So let's just copy this one here. So hover here, say something else like green, and let's see what happens now. And now it turns green. And that's because now this selector here has a higher specificity than this one, right? Because of course this one here, this part is the same as this, but then we add one pseudo class, and so all of a sudden this one here is more specific, and then it applies. So you see that not only we have to make sure that we have the hover pseudo class in place if you want a hover effect, also the selector should have a higher specificity than the original one, which in this case is this one. This usually isn't a problem, but believe me that it happened to me a couple of times that I was writing some really complex navigation in one of my sites, and all of a sudden the hovers weren't working, and nothing was really working as I was expecting. And so I had to learn it the hard way by experimenting a lot and finding out why it didn't work. And so that's why I'm warning you here that you should be careful with your selector specificities. So it's really important that you keep this in mind in case something isn't working the way you expect. Alright, and I hope that with this you now really understood how specificity and importance work, so that you can write better code in the future, and also to be able to debug your code in case something isn't working properly. Because that's also a really important skill when you're writing CSS. Alright, welcome back to yet another theory lecture about how CSS works behind the scenes. Remember that we were talking about parsing CSS, right? First we talked about the cascade, and so now it's time to talk about how values are processed in the CSS parsing phase. We're also going to look at the most commonly used CSS units like percentages, ems, rems, VH, and more, in order to learn how they are actually calculated. But first off, you may ask why this is even important to learn. It is important for a lot of reasons. First, because each time you use a unit other than pixels, like rem or VH or some other relative unit, you need to know that it will ultimately be converted to pixels. And you also want to know how that happens. Also, knowing this stuff will help you predict and control better which property takes which value in the end. So ultimately, if you want to become a serious CSS developer, it's just good to know how all of these pieces fit together to render a final website in the end. So this is what we're going to do in this slide. We will analyze how these 5 CSS declarations build this small element in the bottom of the slide here, and in particular, how exactly the declared values are processed in 6 different steps, starting from the declared value all the way to the final actual value. So we're going to analyze the width, padding, and font size in order to see what's going on here. So let's start with the paragraph's width, which you see has 2 declared values, 100 pixels from the P selector and 66% from the amazing class selector. So these are our declared values. They are actually conflicting. So what is used to determine which one will apply? That's right, it's the cascade. And in this case, it's quite simple, because the amazing class selector is more specific than the P element selector, right? This means that the width of 66 will be applied, and it is therefore our cascaded value. Now, of course you don't need to know every single technical name I'm going to show you here, but if you ignore the jargon and the more technical words, then you will see how this is actually all quite simple. Alright, so next up in the sequence, there's something called the specified value in the official CSS specification. And this one is the default value of a certain CSS property. In this case, it's not really relevant because we have a cascaded value already, but we'll come back to this later. Next, there's the computed value. In this step, values with relative units are converted to pixels, so that they can be inherited, but more on inheritance later. Also, CSS keywords like orange, auto, boulder, and a lot more are computed and replaced here in this step. Here in this case we have a percentage value, which is technically not a unit, and so nothing happens in this step. Next up is the so-called used value. In this calculation step, the CSS engine uses the rendered layout to figure out some of the remaining values, for example percentage values that depend on the layout. And that's actually the case here, because the 66% that we specified is in relation to its parent element, and so the parser needs to know that width in order to calculate the paragraph's width, right? So the section's width is defined as 280 pixels, and so 66% of that is 184.8 pixels. And this is now our used value. Now technically this step 5 and the next one only happen in the rendering phase of the page, but that's not really relevant in order to understand this logic. Now, browsers usually cannot really display 184.8 pixels. That's just way too specific, and so usually a value with a comma like this is simply rounded, in this case to just 185 pixels. And that is, after all these calculation steps, the so-called actual value, which is now ready to be used in the layout. And so the actual value, as we've seen here, is usually obtained by considering the browser and device restrictions. Cool, so now you know how this works behind the scenes of CSS. Awesome, that's great progress. So let's now take a look at the padding property for the paragraph. Now you're probably thinking there is no padding property there, right? And it's actually true that we didn't declare it, but it still has to have a value, okay? That's because in each element on the page, each and every CSS property needs to have a value, even if we don't even declare it at all. So, for padding, we have no declared value and also no cascaded value. But we do have a specified value, and that's because each CSS property has something called an initial value, which is simply the value used if there is no cascaded value. So basically, if we don't declare a value, and if neither the browser nor the user define a value, then the initial value will be used. Actually, inheritance also plays a role here, but let's leave that for later, okay? Now, different properties have different initial values, of course, and for padding it's 0 pixels, which makes a ton of sense actually, because if we declare no padding, that should probably mean that we don't want any, right? And so it's 0. And that's it. There's no more calculations to do because it's already an absolute unit, and so the computed, used, and actual values are all just 0 pixels. Alright, now about the root font size. This means the overall font size of a document. we didn't define it anywhere, right? So again, there is no declared value. However, this is different from the padding property that we looked at before. That's because for the font size, the browser usually has a default value of 16 pixels. Remember how we said earlier that CSS could come from different sources? Well, in this case, the font size is a user agent declaration, and therefore the result of the cascade is these 16 pixels that the browser has declared for the font size. And so, this is our cascaded value. Again, there's no more calculations needed, and therefore 16 pixels is also the used value. Next, let's analyze the section's font size. And now we actually do have a declared value of 1.5 rem. Remember that rem is a relative unit, and so it needs to be converted to pixels by the engine. So the cascaded and specified values are still 1.5 rem, but the computed value is 24 pixels. And why is that, you may ask? It seems a bit random, right? It's because the rem unit is always relative to the root font size, which is 16 pixels in this example, as we saw before. And therefore, 1.5 rem is 1.5 times 16, which is 24. But I'm gonna explain this in more detail in the next slide, don't worry. Alright, and so 24 pixels is our final actual value as well. And now the last one, the font size of the paragraph. Once more, looking at the code, we can't find a font size. So how come the text still has a font size? Well, in this case, it's no default and it's also no initial value, but it's a mechanism called inheritance. Now I'm going to talk in great detail about inheritance a bit later, but what you need to know is that some properties like the ones related to text, such as font size, inherit the computed value of their parent elements. It works like this because it's actually extremely useful. Imagine you'd had to specify the font size on each and every element. It wouldn't be really practical, right? So we just need to define it on some parent, and the children will then inherit it, unless we declare something else, of course. So again, we talk about inheritance a bit later, but this is the most important lesson about it. Alright, and so these 24 pixels we inherited from the section div are our specified value, and of course it's all the same down to the actual value. Pooh! Wow! This was a lot to take in. It's great that you're still with me at this point. Good to see you're really willing to learn this stuff. In this slide, I want to show you in great detail how the CSS engine converts relative units to pixels in order to calculate computed and used values, because this is crucial to know when you write your own code. So this has actually a very practical application in the real world, as relative units are fundamental to build modern responsive layouts, as you'll see when we continue with the project. So again, I have a small code example here for you, so I can show you how different units work in different situations. So we have some global CSS code for the HTML, then a header, and then an element inside the header called header child. That's the basic structure. Alright, so we start with percentages. And there's a distinction between using percentages for fonts or for length or distance measurements. Now again, the percentage is technically not a unit, but to make things easier, we'll simply treat it as one, okay? So in the header, we have a declaration that says font size 150%. And what that means is that the element will have a font size 150% larger than its parent element. In this case, the parent element is simply the HTML or the body, with a font size of 16, and so the header will have 150% of that, which gives us 24 pixels. And that's how it works. Quite simple, right? Now, for length, expressed in percentages, it works a bit different. When we express a length measurement in percentages, like a height, a padding, a margin, or something else, the reference is always the parent element's width. Like in our example, where the padding of 10% results in a used value of 100 pixels, because the parent element has 1000 pixels of width, and 10% of 1000 is of course 100. So, never forget that the parent's width is the reference for percentage-based calculations. Believe me that I learned this the hard way through a lot of confusion and experimentation. Next up, we have some font-based relative units, em and rem. And again, it's different to use ems for fonts or for length. So, both ems and rems are font-based, but the difference between them is that ems use the parent or the current element as a reference, while rems use the root font size as the reference. So let's see how it works. If we want to use ems for font sizes, then the reference is simply the parent's computed font size, similar to what happens with percentages. In our example, a 3em font size on the header child element results in 72 pixels, simply because that's 3 times the parent's font size, which is 24. So 3 times 24 makes 72. Makes sense? Now, for length, it's just a bit different. The 2em padding on the header, since it's a length measurement, uses the font size of the current element as a reference. And we already know that's 24 pixels, and so 2em will result in a 48 pixel padding. Got it? It's a subtle difference, but an important one. So for fonts, the reference is the parent. For length, the reference is the current element. And now finally about the rem. It actually works the same way for both font sizes and length, because it always just uses the root font size as a reference. This means that the 10 rem padding we have here will result in 160 pixels because the root font size is 16, and 10 times 16 is of course 160 pixels. So that's the big difference between ems and rems. Now you may ask, why should we actually size stuff with ems and rems if they are based on font size? That seems a bit strange, right? And the answer is that by doing so, we can build more robust, responsive layouts, because just by changing font sizes, we will automatically change length since they depend on a font size. And that gives us a lot of flexibility, and it's just a great technique. And so we're actually going to do that in practice in a project so that you can see how powerful this approach is. Now finally, we have 2 more relative units, but they are really simple. These 2 are based on the browser's viewport and are called VH and VW. Basically, one VH is just 1% of the viewport height, and one VW is just 1% of the viewport width. So when we specify a height of 90 VH, this will simply translate to 90% of the current viewport height. Of course, in this specific example, we don't know what the viewport height is, but the browser who is painting the page knows about it, and so it does these calculations when it's calculating the used values in pixels. And the same applies of course to VW. So a width of 80 VW, for example, is just 80% of the viewport's width. You probably already used the VH unit before, right? That one is really useful to build these nice hero sections with 100% of the viewport's height. So that's where we use them a lot. Alright, let's now quickly summarize what we learned in this lecture. Maybe you can even print this out if that makes learning easier for you. So, each CSS property has an initial value which is used if nothing else is declared and if there is no inheritance. But we're going to talk more about inheritance in the next lecture. Browsers specify default font size for each page, and that's usually 16 pixels. And this is a user agent definition, so it's not an initial value coming from the CSS specification. Percentages and relative values are always converted to pixels in order for the CSS engine to be able to render the page on the screen. About percentages, they are measured relative to their parent's font size, if used to specify font sizes. And they are measured relative to their parent's width, if they're used to specify length. Now, ems are measured relative to their parent's font size, if used to specify font sizes. And they are measured relative to the current font size, if they're used to specify length. Next, rems are always measured relative to the document's root font size that I mentioned before. And finally, VH and VW are simply percentage measurements of the viewport's height and width, respectively. Okay, and so this wraps up this lecture, which was rather intense, I know, but still super important in my opinion. If anything is not 100% clear, I would actually advise you to watch the lecture again, or at least parts of it, so that everything makes sense for you. Then after that, let's just move on to the next lecture, where we're going to talk about inheritance that we only touched very briefly in this lecture. Well, I wanted to do this in 1 or 2 lectures, but I actually need a part 3 to explain how CSS is parsed. And so this lecture is about inheritance, that we touched upon briefly before, but now we're ready to really dive in. So, inheritance is a way of propagating property values from parent elements to their children. Once more, we have a very simple example here. This time we're going to determine what the line height of the child element will be. So, start by remembering from our previous lecture that each and every CSS property must have a value, even if neither we, the developer, nor the browser do specify it. In that case, there's no cascaded value, right? So, when processing a certain property for a certain element, such as the line height, the first question that the CSS engine asks is if there is a cascaded value. And if so, then of course, that's the value that's used. Now, if there's no cascaded value, then the next question is if that property can be inherited. And that depends on each property. There are some properties that are inherited and others are not. In the case of line height, that property gets inherited, as we can see from the property specification. So, if a property is inherited, then the value of that property becomes the computed value of its parent element. Now, it's very important to note that the value that gets inherited is not simply the 150%, but the computed value. In this case, that's 150% of 20 pixels, which is 30 pixels. And so the line height in the child element will also be 30 pixels, not 150% of the 25 pixel font size. Got it? So again, it's not simply the declared value that's passed, but the computed value. Now, if it's a property that's not inherited, like for example padding, then the specified value will become the initial value, which is also specific to each property. In the case of padding, that's just 0 pixels, like we actually saw in the last lecture. Again, you don't need to memorize these initial values, because they are all just rather intuitive. So, just like before, here's a quick summary of what you need to know. I guess the most important thing to know about inheritance is that it's there, and that it passes the values for some specific properties from parents to children. Again, if you just ignore the jargon, inheritance is actually pretty straightforward. Inheritance allows the developers to write less code and code that will be more maintainable. Now, in the specification for each and every CSS property, you will find if the property is automatically inherited or not. As a rule of thumb, properties related to text are inherited, so properties like font family, font size, color, etc. Other properties like margins or paddings are of course not inherited, because that would just be extremely impractical. Just imagine setting a margin on some section or something, and then suddenly all of the children would automatically get the same margin. That doesn't make any sense, right? Now, it's also important to remember that what gets inherited is the computed value of a property and not the declared value. Also, inheritance of a property of course only works if no one, neither the developer nor the browser, declares a value for that property. Okay, now something else I didn't mention yet is that we can use the inherit keyword to force inheritance of a certain property. And I will actually show you that when we get back to coding. Also, in the same way, the initial keyword can be used to reset the property to its initial value. And that's actually it about inheritance. Not hard at all, right? So let's move on now. Hello there! Let's now put some of the stuff we've been talking about into practice by going back to our project and convert all our pixel units to RAM. And I'll explain you why, of course. So in this lecture, you're going to learn how and why we use RAM units in our project, and why you should do the same. And of course, a workflow to convert pixels to RAM in the easiest way. So this is what we're going to do in this lecture. We will change all the absolute pixel units to relative RAM units, okay? And why are we going to do that? Well, it's quite simple actually. It's because we want an easy way to change all the measurements on our page with one simple setting. For example, when we hit a breakpoint to display our page on a mobile device. When that happens, we want a way to decrease all the measurements in our site at the same time. And instead of writing hundreds of lines of code in the media queries, we can just change one global setting. And that is the global font size. So let me show you how this awesome technique works. So you remember how the RAM unit is always in relation to the root font size, right? So if we now set that root font size, we can then very easily change all the other measurements on our page to RAM. So let's do that. So the root font size is set in the HTML selector, okay? And so we say font size 10 pixels. Not the 16 that we had before, but 10. I'm actually going to remove this one, but just commenting it out so it stays here for you to see. And so yeah, so I changed this to 10 pixels. But now, why did I change it to 10 pixels? Well, we do 10 pixels here in order to make our life easier, to be honest. That's because now we know that 1 rem equals exactly 10 pixels, right? Because remember, 1 rem is exactly the root font size. So if 10 pixels is now the root font size, then 1 rem is 10 pixels. And so now it's really easy to replace all the pixel units with rem. Because all we have to do is to divide all the pixels by 10, and that's our RAM, right? Now if it was 1 RAM is 16 pixels, then we would have to make a lot of calculations. And we don't want to do that, of course. So this is a pretty common technique to avoid that, okay? So with this in mind, let's actually do that. So we start here at the top and change all, or let's say most, of our pixel measurements to RAM. So we have a 30 pixel padding. So just divide it by 10 and you end up with 3 RAM. Okay, and that's it. So let's keep looking. What do we have here? Oh, another one, 40 pixels. So it's 4 RAM, right? So you don't have to do any calculations. You just divide it by 10. 4 RAM. And here, 3.5 RAM, right? It makes sense, right? And I will actually show you the effect of this in a second, okay? So here we have percentages, nothing changes. Here, 6 RAM. Here again, 6 RAM. And here 3.5 RAM. Font size here should be 2 RAM. Here it's 1.74 RAM. Well, that's a bit specific. Let's just keep it at 1.7 RAM, okay? Or we can say 1.75 RAM. Okay, that looks acceptable. Now here we have minus 10 RAM. Here just 1, and 10, and minus 1, okay? So ideally, of course, you start by doing this right in the beginning of the project. But I didn't want to overwhelm you and to scare you with all too much theory right at the beginning of the course. And so we just started the simple way, and the way you probably already know how to do everything, which is in simple pixels. But if you're doing responsive design and modern CSS development, then it's really good practice to use relative units like RAM. So here we have 3 RAM. Now of course we could also have used Ms instead of RAMs, but that's a whole lot of work, believe me, I've tried it, and it's really difficult to make. Because remember that the Ms depend not on the root font size, but on the font size of the parent element. And with that you have to do a lot of calculations, and it becomes really difficult to manage. So I always set everything to RAM, and then it's really the best solution. 1.5 RAM, 4 RAM, and 10 RAM, of course. Here, we can also do it here in these box shadows. Here, it's 0.5. So whenever you have a point, you don't write out the 0 in CSS, okay? So of course you can, it works, but it's a, like, let's say a coding practice to only put the dot, okay? It's just a good practice that professionals use. So 10 RAM in here. Any more pixels? You know, that's it. All right, so let's now take a look and see if everything is still working the same. All right, great. The only thing is here, the text size here, because originally we set it to 16 pixels, right? And so now here we actually have to set the font size. Well, yeah, here it is. So if we still want it at 16 pixels, then it should be really easy, right? So 16 pixels is 1.6 RAM. So let's go back. And here we go. Great. Now what I want to show you is this. So if we now go ahead and just change the overall font size, so yeah, here it is, then see how the entire design changes. So I go down to 9, and you see that everything changes, everything became smaller. Take a look at the padding here outside, at this padding, and here at this size, and also the text size, as I will decrease it further. Sorry, this was increasing, so I decrease it further now. So everything is becoming smaller, right? And that is amazing once we start writing media queries. It will make our lives so much easier. So imagine we had now this smaller version like on a phone, and then this would already take a lot of work from us. Instead of writing all the media queries to make all the font sizes smaller and to make all of these distances here smaller, like these 30 pixels, this now automatically converts to something else. For example, in this, well, this is now really small. Let me check this. Where is it? This body. It has now a padding not of 30 pixels, but of 15 here, as you can see down here. You see, now it's 15 pixels and not the 30 that it was before. And that's because we set the font size here to 5. Right? So 5 is half of 10, and so 15 is half of 30. Right? If we put it back like to 8, then the padding becomes 24, and so forth, and so on. And the same would, of course, work in the other direction. So imagine we have a really huge screen or something, and we want to increase our design. Or someone zooms in the page, and that's what happens. So we can also write media queries for larger screens and then increase the design. Alright, so that is the trick. And the huge advantage of using RAM. Now we can still improve this because it's actually a very bad practice to set the font size to pixels as well. So up here, this shouldn't really be 10 pixels. It should be something else. The problem is that by doing so, we actually override the browser font size setting that the user can manually change in the settings. And many people actually do that. For example, when they have bad sight and cannot see so good, then some people actually increase the default font size of their browser. Now, if we set the font to like the 10 pixels like we did here, then we remove the ability for these people to see our website properly, because they can no longer change the default font size. Well, they can, but our root font size will not be affected by that anymore. It will just be 10 pixels no matter what the user has as a default font size. So this is really a bad practice. And that is why we're going to set the overall font size to a percentage here, which will translate to a percentage of the font size given by the browser. Now the default font size, if the user doesn't change anything, which is the initial situation that we want, is 16 pixels. So that's the absolute default. And that's the situation that we're counting on here. So if we put 100% here, this would mean that the root font size would be 16 pixels if the user doesn't change anything. And if the user does change the default font size, let's say to 18 pixels, then the root font size would be 18 pixels. If it changes to 20 pixels, then it would be 20, and so on and so forth. Now, but we don't want 16 pixels here, right? What we want is 10 pixels. And so it's very simple. All we have to do is to divide what we want, which is 10, by 16. So I'm having a calculator here. So 10 divided by 16 is 62.5%. And that is what we're putting here. 62.5%. And that's it. That's the whole technique. So now imagine, let's say 0.625. So if the default is 16 like we had before, then this translates to 10 pixels, right? Which is what we want. But if the user changes to, let's say, 20 pixels, then our default font size will be 12.5 pixels. So the root font size, I was saying. And if the user does 22, it goes to 1375 pixels, and so on and so forth. And so with this, we allow the user to actually zoom in on the page automatically, not only to change the font size, but to also zoom in on the page, because basically that's what happens. Not exactly zooming, but increasing all of the measurements that we have on our page. So make sure that you understand this technique. It's really widely used in the CSS developer community because it's so simple and yet so powerful, as you saw. Now, one thing that I should probably tell you is that RAMs are not supported below Internet Explorer 9, okay? So if you have to develop a site for one of these browsers, so the really old Internet Explorers, then you cannot use RAMs because your site will simply not work at all, okay? Now, since that applies to almost everything that I'm going to show you in this course, I guess that's not really relevant at all. Because if you're interested in taking this modern course that you're taking right now, then you're probably not trying to develop for these old browsers anyway, right? Alright, and one more thing we can do before we finish this lecture is to use the power of inheritance, since we already talked about inheritance, right? So whenever we can use inheritance, we should use it instead of using here something like the universal selector, okay? And so what I'm going to do now is to remove this box sizing from here and put it here on the body. Okay, so now we set the body to box sizing border box, and then in here what we do is to say box sizing, and we use the inherit keyword. And that's it. So remember how we could use the inherit keyword to force inheritance. That's what we're doing here. So the box sizing property by itself is not inherited, but by setting the box sizing property on each and every element on the entire page to inherit, it will automatically inherit whatever we put here on border box. So this is considered a slightly better practice by the CSS community, because it makes it a bit easier to change the box sizing, like in plugins or other components, where we might want to use a different property for box sizing. Okay, so it doesn't make a huge difference, it's just a slightly better practice to do the box sizing border box like this. Alright, and since we're at it, we should actually update this universal reset here, because we can do slightly better than this, which is to also select all of the after pseudo elements and also all of the before pseudo elements. That's because right now only the real elements get this behavior here, but the after and before pseudo elements, they don't get this behavior. And since we don't want to see any strange behavior happening, we will also include these ones here as well. So, you know, we already have a after pseudo element down here, and if we had put a width or a height and then a padding or a border, then it wouldn't have behaved the way we expected it, which we expected because of the box sizing of border box. So actually it's down here. So it wouldn't have worked the way we expected because we actually didn't have this part here in the universal selector in our global reset. Okay, so just another slightly improvement over our previous code. Okay, and that's really it for this lecture. See you in the next video. Welcome back. Do you still remember the diagram that I showed you in the beginning about how CSS works behind the scenes? This one, right? So we've been talking a lot about the parsing phase, but now it's time to move on to the website rendering phase. So this lecture should give you a pretty good overview about how the visual formatting model works so that you can write your code in a way that makes more sense to you. What this lecture will do is maybe not so much give you new tools, but it will summarize a lot of the CSS that you actually already know and put it in a more meaningful context. So, the CSS visual formatting model is an algorithm that calculates boxes and determines the layout of these boxes for each element in the render tree in order to determine the final layout of the page. This model is one of the fundamental concepts of CSS, which is why I decided to include it in the course. Now, in order to do this, the algorithm takes into account factors like dimensions of the boxes, which are calculated by the box model, the box type, which can be inline, block, or inline block, the positioning scheme, which includes concepts like floats and absolute or relative positioning, stacking context, the other elements that are present in the render tree, such as siblings or parents, and finally, external information such as a current viewport size, dimensions of images, or other factors. So by putting all of these factors together, the browser figures out how the final website will look for the user. So let's now look at the first 4 of these factors in more detail. And let's start with the box model. The box model is without a doubt one of the most fundamental parts of CSS, and it's something you really have to master in order to lay out a web page. The box model is one of the factors that define how elements are displayed on a web page and how they are sized. according to the box model, each and every element on a web page can be seen as a rectangular box. In each a width, a height, a padding, margins, and a border. But note that they are all optional, so there can be boxes with no margins or no paddings at all. Now this image here shows us how the box model works. So let's break it down. First, the content of a box is where all the text, images, or other content that we specify go. We can easily define its height and width using the corresponding CSS properties, as we're going to see in the next slide. Next, the padding is a transparent area around the content, but still inside of the box. We use paddings to generate white space inside of a box, and we can define the padding by specifying the padding property in CSS, as I'm sure you already know. Next, we can specify a border for a box, and that border goes around the padding and the content. Similar to the padding, we have the margin, but instead of being inside the box, the margin is white space that's actually outside of the box itself. So we can think of margin as the space between boxes. So, for example, if we want some space between two elements, we will define their margin properties in CSS. And finally, there's something called the fill area. Remember how the text content in images go inside the content box? The same does actually not apply for background images or the background color of a box. These properties will be applied not only to the content box, but to the entire fill area, which also includes the padding and the border, but not the margin. Alright, so let's now talk about heights and width in the default box model. As I mentioned, we can specify the height and the width of an element. Now, if we choose not to specify the height or width of a certain element, the visual formatting model will just use the content of the box to determine its size. So let's now take a look at how the default box model calculates heights and width of block level boxes, and more about block level boxes or elements later. So, the width of a box, as we will see in the final layout, is defined by the right border plus the right padding plus the specified width plus the left padding plus the left border. And the same logic, of course, applies for the height of the box. But let's look at a quick example to make this more clear. Suppose we define the height for an element of 100 pixels and a padding to the top and bottom of 20 pixels. So the final height, as displayed on the website, would be 140 pixels. This means that whenever we define a width or a height of a box, the padding and border get added to what we defined. But that doesn't sound very practical, right? So the solution to fix this problem is to use the box sizing property with the value of border box. And I'm sure that many of you already know and use this trick, and I also showed it in my beginner HTML and CSS course. But it's still important to remember how this actually works. So, if we set box sizing to border box, the height and the width will be defined for the entire box, including the padding and the border, and not just for the content area. What this means at the same time is that the paddings and borders that we specify will of course reduce the inner width of the content area, instead of adding them to the total height or width of an element. Alright, so if we look at the height and width calculations now, in this case, the actual total width of a box is equal to the specified width. And the same goes for the height. So if we now define some paddings or borders, they will not get added to the dimensions of the box, which makes our lives so much easier. And if we look at our example now, the final height would of course be 100 pixels, just as we specified for the height of the element. Alright, so we looked at the box model and how height and width of boxes are calculated. But this applies mainly to block level boxes, which is one of the different types of boxes in CSS. So let's now look at the three most common and most important box types, and how different box types determine how boxes are laid out on a page. Let's start with the block level box or element. We can say both. Now, first off, the type of a box is always defined by the display property, which I'm sure you know already. So in the case of the block level element, the display property is usually set to block. But please note that the values flex for flexbox layout, list item, and table also produce block level boxes. Now, all HTML elements have a default display property, and elements such as paragraphs or divs, which are usually formatted visually as blocks, have their display property set to block by default. We can always, of course, change this property manually, which can be very useful in some cases. Okay, so being a block level box, this box will always occupy as much space as possible, which is usually 100% of its parent width, and create line breaks after and before it, meaning that blocks are formatted vertically one after another. Now, about inline boxes, they are basically the opposite of block level boxes, because their content is distributed in lines, meaning that an inline box only occupies the space that its content actually needs. Therefore, they also don't cause line breaks after or another them, but instead, they just sit inside their block level parent element. Now, about the box model, things work a bit different in inline boxes. First, the height and width property do not apply, which means that we cannot use these properties here. And second, we can only specify horizontal paddings and margins on inline elements, so only on the left and on the right side. That's the way the box model works on inline elements. So of course this has some serious limitations, and in order to overcome them, there's another type of box, and that's the inline block box. Now, inline block boxes are technically also inline boxes, but which simply work as a block level box on the inside. So since they are technically inline elements, they also use up only their content space and cause no line breaks. But since they work as a block level box on the inside, the box model applies to them just like in the regular block level boxes. All we need to do in order to set an element to an inline block is to set its display property to inline block. And that's it. Very easy. So it's really important that you understand the difference between these three types of boxes so we can use them as needed in different situations. Okay, next up we have positioning schemes. And there are three of them in CSS: the normal flow, floats, and absolute positioning. And I'm sure you're already familiar with floats and absolute or relative positioning, and so this is more to bring all of these properties together into a bigger context. So, the normal flow is what happens to an element if you don't do anything to it at all, if you don't float it, and if you don't use position absolute on it. If you use position relative, then the element is still in a normal flow. And what the normal flow means is that the elements are simply laid out on the page in a natural order in the code. The next positioning scheme is when you use floats. The float property causes an element to be completely taken out of the normal flow and shifted to the left or right as far as possible until it touches the edge of its containing box or another floated element. When this happens, text and inline elements will wrap around the floated element. Also, when an element is floated, its container will not adjust its height to the element, which sometimes can be problematic. The usual solution to this is to use clear fixes, which I'm sure you have used when building layouts using floats, right? And then finally, there's absolute positioning. And just like with floats, when you set the position property to absolute or also to fixed, the element is taken out of the normal flow. Now, what's different here is that with absolute positioning, the element has no impact on surrounding content or elements at all. In fact, it can even overlap them. So if we want to position an absolutely positioned element on a page, we use the CSS properties top, bottom, left, and right to offset it to its relatively positioned container. Now, as I mentioned, an absolutely positioned element can overlap other elements occupying the same space. And how do we solve this? Well, CSS solves it for us actually, using something called stacking contexts. So there's one piece left in the puzzle of the visual formatting model: stacking contexts. So, stacking contexts are what determine in which order elements are rendered on the page. A new stacking context can be created by different CSS properties, where the most widely known is z-index. But there are other properties that also create new stacking contexts. Now, stacking contexts are like layers that form a stack. Layers on the bottom of the stack are painted first, and elements higher up the stack appear on top, overlapping the elements below them, just like you see on the slide. In this example, we have three stacking contexts, because each element uses the z-index property on an either relatively or absolutely positioned element. And that's one way of creating a new stacking context. Now, between these elements, The one with the higher z-index appears on top, and the one with the lowest z-index appears at the bottom. Now, a common misconception is that only the z-index property creates new stacking contacts, but that's not the case. An opacity value different from 1, a transform, a filter, or other properties will also create new stacking contacts. That's why sometimes, even with a z-index set on a positioned element, the stacking order doesn't work as expected. But as with everything we talked about in this section, we will see practical applications of all of this in the coding part of the course. Hey there, welcome back. This is once again an extremely important lecture because we're going to talk about CSS architecture and how we should think about layouts and how we should mark up our code in a professional way. So this one is technically not about how CSS works, but it still made sense to put it here in this section. So remember that we want code that is clean, modular, reusable, and that makes it easy to add more and more features to our web page or app if it needs to grow. So because of all of these reasons, we cannot just dive into a new project and leave architecture behind, just as a second thought. Instead, we need to take important decisions concerning our HTML and CSS code right from the beginning of the project. And that's what I want to help you with in this lecture. So we need a good strategy here, a good mindset. And from my experience, the best strategy is something I like to call the think, build, architect mindset. We need to think about the layout of our web page or web app before we actually write the code. After having the layout figured out, we should build it in HTML and CSS with a consistent structure for naming our classes. Also, at the same time, we should create a logical CSS architecture by using multiple files and folders. So, starting with the think part, I like to use something called component-driven design, which is actually a principle that is used across all software development. In CSS, with component-driven design, we try to divide our page into modular components. So, what are these components? Components are the building blocks that we use to construct our interfaces. So we can basically think of our interface as a collection of components, held together by the overall layout of the page. Probably the most important thing about components is that they should be reusable across a project and also between different projects. That's really important. So you can build a library of your components and then reuse them across projects, which will speed up your development. Plus, components should be independent so that we can use them completely on their own, no matter where on the page. What this means is that components should not depend on their parent elements. Once again, all of this will make your CSS code easier to maintain and to scale if necessary. Now, of course, these are rather general rules, and they can be broken if it's strictly necessary, as long as you have a good reason. Now, I don't want you to memorize anything here, okay? This is just a discussion that we need to have in order to become better CSS developers. Over time, with practice, all of this will become really intuitive to you. And of course, we're actually going to apply this in a Naders project that we already started coding. Alright, and just as a side note, this whole thinking component strategy is actually a bit similar to Brad Frost's super popular atomic design philosophy, which maybe you have heard of by now. So according to atomic design, the smallest units on a page are atoms, which together form molecules, which combine together form organisms. And these organisms can be seen as our components in some situations. Now, we're not going to focus so much on atomic design in the course though. I just wanted to let you know that there are other ways of thinking about our interfaces. And you can take a look at atomic design if you're interested and if you haven't heard about it. Alright, so after thinking about our design, we need to code that design using HTML and CSS. And in this step, it's important to have a consistent strategy, a structure for naming our classes. And there are many approaches for naming classes, things like object-oriented CSS or SMACS, but the one I like the most is BEM, which is becoming more and more popular by developers around the world. It's a nice clean system for marking up our layouts. So, BEM stands for block, element, modifier. And this is how class names usually look like using the BEM methodology. So if you've ever seen code that looks like this example here, now you know that it uses the BEM system. So first, in BEM, a block is a standalone component that is meaningful on its own. And what this means is that the components we defined in the last slide are the blocks in BEM. In this example, the recipe is a block and also the button, because both of them are standalone components that can be reused anywhere in the project. And note how these two blocks are actually nested. So the button block is inside the recipe block, and that's perfectly normal and acceptable. Next, an element is a part of a block that has no meaning on its own. So in our example, that could be the info panel or the stats box. But there are lots of other elements there. But again, if we take one of these elements out of the block, then they wouldn't be useful at all. They wouldn't have any meaning. Now what's important to note here is how the recipe block still appears in all the class names within the block. Do you see that? That's why we have the word recipe all over the place in this HTML code. Also, notice how this creates selectors with really low specificities, because we always use classes and they are never nested, and so they always have a pretty low specificity. And this is one of the big reasons why BEM is so widely used for easy to maintain and reusable code. Alright, and last we have the modifier. And the modifier is a flag that we can put on a block or an element in order to make it different from the regular blocks or elements, to make a different version, let's say. In our example, we have a modifier to make the button round. So for instance, there may be some rules for all buttons, and then we use a modifier to make a more specific, a different button, and in this case, a round one. Now try to read that entire HTML markup I just showed you, okay? Seriously, try to stop the video and read the code. Because just by reading the markup with these class names in it, you can instantly see how all the elements are related and what each of them does. Now imagine this with a whole page, and the effect would become even better. Now again, you're gonna get used to all this once we start using it in practice throughout the project, in one of the next lectures. Alright, and just to finish this part, I know that many people really hate BEM because they say it looks ugly and it's hard to write. And yeah, I agree that it might look a bit funny actually, and that you might have to type a bit more code. But believe me, that is really worth it. And you should absolutely try it with me once we start coding again. And now the last part of our strategy, which is architecting CSS. And remember that by that I mean to create a logical folder and file structure for our CSS to live in. Once again, there are different options here, like the itCSS method or SMAX, but I like to use something called the 7-1 pattern, introduced by Hugo Giraudoux. I'm not sure if I spelled his name right, but let's hope. Okay, so the 7-1 pattern is extremely simple. All it means is that we have 7 different folders where we put partial SASS files, and then one main SASS file in which we import all of our partial files into one final compiled CSS style sheet. Of course, when I say SASS here, I could mean any other CSS preprocessor, because all of them allow to implement this pattern, okay? And we'll see how that works in practice once again a bit later. So the 7 folders I mentioned that are used in this method are the base folder, where we put the basic project definitions, the components folder, where we have one file for each component, the layout folder, where we define the overall layout of the project, the pages folder, where we have styles for specific pages of the project, the themes folder, if we want to implement different visual themes, the abstracts folder, where we put code that doesn't output any CSS, such as variables or mixins, and finally, the vendors folder, where all third-party CSS goes. So that's just a big overview, but I'll go into further details about these folders once we really implement them in the project. Now, we don't always need to use all of these folders, and that's gonna depend on the size and the scope of the project. Alright, and that's it about CSS architecture, BEM, and component-based design. I hope this made sense to you, and that you can see and appreciate the huge value that these techniques can add to our workflow. I'm sure that putting this into practice will help with that. So stay tuned for the next lectures where we're gonna do exactly that. To finish this section, let's put something that we learned in the last lecture into practice right now. And that's to convert the HTML we've been writing so far into the BEM system, so that we can start using BEM from now on. So in this lecture, you're just going to learn how to use the BEM method in practice. And there's actually not a whole lot to do here already, because we haven't written so much HTML up until this point. One thing that we have to do though is to identify our first block here, and that's the header here, okay? So the header is obviously a block in the BEM system, because it is a standalone component that is meaningful on its own. And so it's a block, and so all the elements that are inside it should also have the header attached to them, right? So this logo box here, it can only really exist here in this header. And so it's an element, right? Because it's part of a block, but it has no standalone meaning. And so we should now start adding the header to the elements. So header, and now remember, it's double underscore to separate the block from the element. So header is the block and logo box is the element. And the same thing here for logo. So we call it header logo. Because this logo with this exact size and this exact image, it only just exists here in the header. The same goes, of course, for this text box. So header text box, simply because this text box is a part of the header and it doesn't make much sense to use it anywhere else. Now, as for this heading primary here things are a bit different actually, because we could treat this as a block on its own. Imagine that we wanted to use this h1 element somewhere else. Imagine we had another page, but without a header like this one, and we wanted to use this primary heading. We could of course do so. And so this one here is a standalone block. Now, as for these two here, what do you think about them? They're called heading primary main and heading primary sub. So what these two are, they're actually modifiers of the heading primary, right? Because they simply create a slightly different version of this heading primary class of the block, right? And so what we do is that we put two dashes here. So remember, block, and then if we have a modifier, we do dash dash and then the name of the modifier. If it's an element, then we use underscore underscore and then the name of the element after that, right? Okay, same thing down here. A button is of course a standalone component, so we can consider it a block in the BEM notation, of course, because we're going to use this button throughout this entire page. Now here, these two can be considered flags as well, such as we had before, right? And so we use double dash on both of them. Because this is still a button, but they do simply create different versions, different modifications, and that's why they're called modifiers, right? And that's actually all we have to do here in this markup. So we now have this converted to the BEM notation. So let's just go back to the style and change it here as well. So header, and let me just actually copy this part. So header, then here we had header logo and header text box and heading primary, okay? So here, just a dash missing, another dash. Here everything stays the same. Button, everything is good. So here another dash to create this difference. And here for the animated. All right, that's actually it. So our code is now converted to BEM. Let's just check if everything is the same here, which of course it should. And well, something happened here, so something is clearly wrong. So let's go back to check if our CSS is completely correct. So let me see if I forgot something here. Primary sub and main. Okay, so here the T is missing. I guess that was the problem. It probably was. Well, there's another bug somewhere, I guess. Ah, okay. That's because I put the T in there accidentally. Alright, but now it should work. And here we go. So everything is back to the same. Our code is now converted to BEM and we're good to go. And that actually wraps up this theoretical section. I believe that it was rather intense and rather sometimes hard to grasp. But as I said so many times already, I know that it's really important to go through these more theoretical and fundamental aspects of the CSS language if you really want to grasp it and become more professional in it. So great job, great progress. It's amazing that you're still with me. and you now deserve some break or some rest if you need. Well, and if you don't, then just continue to the next lecture and I'll be waiting there for you.